In this video, we're going to look at the Buckingham PI Theorem. So what is the purpose of the Buckingham PI Theorem? The purpose of this theorem is to identify consistent sets of dimensionless groups that are relevant to a problem. So this is the technique that was used to generate all of the dimensionless groups that we've seen in the introductory lectures up to this point. So first thing I'm going to do is just go through the procedure. And it's about a 7 or 8 step procedure, and we're going to list each of those items out here. And then we'll do an example where we apply Buckingham PI Theorem to calculating the drag force on an object. So first of all, the procedure. Well, the very first step is to identify the dependent variable. And by that I mean, what quantity are we interested in studying? So the example we're going to do here in a little while is the drag force on an airfoil. So the drag force would be the dependent variable. In other words, the variable that is dependent on several other things. So step 1, identify the dependent variable. The second step is to list all of the independent variables. So this is very much a process of trying to figure out or trying to imagine what all of the things are that could affect the dependent variable. So we might come up with a very, very long list of independent variables, depending on the complexity of our problem and depending on how thorough an analysis we want to do. But step 2 is just listing the independent variables. The next step is just count the total number of variables. So that's a relatively straightforward step, but notice we're counting the total number here. So the independent variable plus all of the dependent variables. So this just tells us how many variables are involved in this problem. Next thing we want to do is list the dimensions of each variable. So independent and dependent variables. Just make a table or whatever works for you where you list all of the dimensions of each variable. And again, we'll see how this works when we do our example in a little while. So that's the first 4 steps. Step 5 is to count the number of unique dimensions involved. So depending on the problem that we're looking at, all 4 of our fundamental dimensions, mass, length, time, and temperature, may not be involved in the problem. So when we count the number of dimensions involved, we're going to get a number somewhere between 1 and 4. Step 6 is to select a certain number of variables from our set of variables that do not form a dimensionless group or a so-called pi group. Now, this is a little bit of a subjective step in this process, and very often there is more than one choice we could make at this point. So I'm going to illustrate in our example what happens if we make different choices at point 6. So this set of j variables is called the repeating variables. And notice the number of variables that we want to select in this stage is g, the number of dimensions that are involved in the problem. So we're selecting a set of j repeating variables. Now, why do they have the name repeating variables? Well, it's because they're going to appear, potentially at least, in every one of our pi groups. So there's some experience required to choose these repeating variables wisely, and we'll talk about that in the context of the examples that we're going to do. Now, because the repeating variables could appear in every pi group, we do not want to choose our dependent variable as a repeating variable because we want our dependent variable to appear in only one place in our final result because we're investigating how that dependent variable depends on all the other things. So we don't want it appearing in a whole bunch of different places. And I'll reinforce that point again when we look at an example. Sometimes at this stage we find that it's actually impossible to select j variables that do not form a pi group. And so that's an important aspect. So if you select your variables and you look at them and you see, you know what, I can actually arrange these j variables into a pi group, then that is not a valid selection for the set of repeating variables. Remember up here, these repeating variables do not form a pi group. They cannot form a pi group. It must be impossible to form a pi group with those repeating variables, or a dimensionless group. Well, if you can't, if there's just no set of j variables that could possibly be chosen that satisfy that criteria, then what you do is you reduce j by 1, and you do step 6 over again. So if j used to be 3, you drop it down to 2. See if you can do that now. And first of all, this happens rather rarely, and when it does happen, reducing it by 1 usually takes care of the problem, and you can proceed on to the next step. So what is the next step? Well, the next step is to form the n minus j pi products. Now, I'm not going to list out the procedure of exactly how to do that here. That's much, much easier to show in the context of an example. But the important thing to realize here is the number of dimensionless groups that we can form is going to be n minus j. And again, we'll emphasize that when we do an example. So at step 7 here, we figure out how many dimensionless groups is it possible to form given the set of dependent and independent variables that we've identified. Most of the work in the Buckingham PI theorem is actually in step 7 here. So the final step after we've formed those pi groups is just to rewrite our function in dimensionless form. So the final result is the function, and by function I mean how does the dependent variable depend on the set of independent variables. Now, it's very important to realize dimensional analysis is not going to tell us what that function is. It's going to tell us what form the function should take, or the most efficient way to express that function in terms of groupings of variables that form dimensionless groups. Now, this 8-step procedure here is much, much easier to see and understand if we do an example or an illustration. So that's what we're going to do. We're going to look at the drag force on an object. Now, it could be any object, but we're going to look at an airfoil. So consider the drag force on an airfoil. And for this situation here, we're just looking at a 2-dimensional case. So imagine that this airfoil extends in and out of the screen to infinity, essentially, and the force that we're trying to find, the drag force, we're finding that force on a per unit length basis. That's why I have a little reminder here. We're finding the force per unit length. And this little primed on here is to remind us this is a force per unit length. So ultimately, if we were to assign some units to this, it would be newtons per meter. And that's per meter of span of the airfoil in and out of the screen. So force per unit length. So what might that force per unit length depend on? Realize this f primed is our dependent variable. That's what we're studying in this problem. We could also do this looking at the lift force, but this illustration we're looking at the drag force. So what does that depend on, or what are the independent variables that we need to look at? Well, certainly the free stream velocity, which I'm going to call v, is definitely going to have an effect on that force. So low wind speed, high wind speed definitely affects the force. We know that for sure. So we better start listing v as one of our independent variables. The density of the air approaching it, or the density of the fluid approaching it in general, is certainly also going to have an effect on the force on that object. It's probably true that the viscosity of the fluid will also have an effect on the force on that object. And also, the size of this airfoil, represented here by the chord length, c, is also going to have an effect on the force on that object. Now, we could continue on here and identify other parameters as well that might have an effect on that force. Maybe the surface roughness on the airfoil, maybe the thickness of the airfoil, or the curvature of one of the surfaces or something like that. We could list a lot of other parameters to identify here. But I'm going to keep it to a minimum here just so that the Buckingham PI theorem is relatively straightforward to apply and the example or the illustration doesn't take too long. And we'll look in a few moments after we've done this one at what is the effect of adding some more parameters on. We will take a look at that. So this is the scenario that we're going to apply Buckingham PI theorem to. we want to figure out the drag force per unit length as a function of all of these other variables: free stream velocity, density, dynamic viscosity, and chord length. So we'll go through the steps of the Buckingham PI theorem now that we've sort of laid out the problem that we're looking at. So first of all, identify the dependent variable. Well, we've already sort of talked about that. That's the drag force per unit length, F prime. So step 1, done. Step 2, identify the independent variables. Well, we've already sort of discussed that as well. It's the density, viscosity, velocity, and chord length. And like I say, if we wanted to do a more detailed investigation of the drag force on this airfoil, we would list more and more parameters there. So that's our dependent and independent variables. So realize what we're investigating here is the drag force as a function of these 4 things. So this is sort of our starting point. And what Buckingham PI theorem is going to do is allow us to rewrite this equation in dimensionless form. So that's the very last step of Buckingham PI theorem, is to rewrite that function in dimensionless form. So realize this notation here just means the drag force is a function of these 4 things. This does not tell us what that function is. It doesn't tell us the mathematical form of this function. We need to do a series of experiments to figure that out. But what Buckingham PI theorem will tell us is how can we rewrite this function so there aren't so many darn things changing on us. Here we've got 1, 2, 3, 4, 5 variables, combining our dependent and independent variables together. When we apply Buckingham PI theorem to this, it'll turn out there's only 2 parameters that are important, but they're dimensionless parameters. Okay, now continuing on with the Buckingham PI theorem. We've done the first 2 steps. The third step is to count the variables. Well, that's pretty straightforward. N is equal to 5. But we do have to remember at this stage to count both the independent variables and the dependent variable. So that's 5 in this case. Step 4 is to list the dimensions of each variable. And there we remember that our dimensions are mass, length, time, and perhaps temperature. So we go and we get our 5 quantities here. So we have our force first of all. What are the dimensions of force? Well, that's mass divided by time squared. What are the dimensions of density? Mass divided by length cubed. Remember that the units of density are kilograms per meter cubed. So that's mass divided by length cubed. Dynamic viscosity has dimensions of mass divided by length and time. Velocity is length divided by time, meters per second. And the chord length, of course, is just a length. So that's step 4, just listing the dimensions of each of our variables, independent and dependent. So the next step, count the number of dimensions involved. So notice, although we have 4 dimensions that are possible over a wide range of problems, there are only 3 dimensions involved in this particular problem: mass, length, and time. There's no temperature. We didn't list any properties here that have temperature as part of their dimensions. Okay? So if we had listed some other property of the air, perhaps like it's a specific heat or something like that, then we would have an additional independent variable and temperature might enter the problem. But for this illustration, the number of dimensions involved is just 3. So J is equal to 3. So we have an N of 5 and a J of 3. So the next step is that one that I talked about where there's some choice to be made, where we have more than one choice on how to proceed, and that's select J variables that do not form a pi group. So just a reminder of what our variables are here. We'll take a look at it in functional form. So drag force as a function of those 4 things. So we need to pick 3 of these that do not form a dimensionless group. And of course, we do not want to pick our dependent variable. So there's really not a whole bunch of choices. What we're going to do in this illustration is select density, velocity, and chord length. And again, a very important feature here is that these three things cannot be formed into a dimensionless group. And the way that we can see that is, of these three quantities, density is the only one that contains mass. So if we go back to our table here, density is the only one that contains mass. Velocity and chord length don't have a mass in them. So there's no way you can arrange rho, v, and c by themselves so that it has no dimensions, because there's nothing to cancel out this dimension of mass in the density. So that's one way to quite quickly tell that you have a valid selection of these j variables to form your repeating variables. Remember, that's what these are called, is our set of repeating variables. If there's one of our dimensions that only exists in one place in this set of three, then that is a valid set of repeating variables. So rho, v, and c is what we'll proceed with here as our repeating variables. So step 7 is to form our dimensionless products, or our dimensionless group, or pi products. And remember, we're expecting to get, or we will get, 2 such dimensionless groups, because n minus j for our problem is 5 minus 3. So this is where we'll show you how to get those groups. We didn't describe that when we just listed the steps of the Buckingham PI theorem, but we'll show how to do that now. So we're going to find 2 of these pi groups. And our notation here is to call these dimensionless groups pi 1, pi 2, pi 3, etc., however many we have. So the way we form the dimensionless groups is, the first thing we do is write down our repeating variables. So we have our 3 repeating variables, rho, v, and c, and we raise each of them to an unknown power. So rho to the a, v to the b, and c to the d. I didn't use c here because c is already being used for the chord length. So these 3 exponents, or powers, are unknown. We're going to show how to find them here in a moment. But that's our first step, is to write out our 3 repeating variables raised to some unknown power. And then we multiply that by one of the other variables. Doesn't matter which one, we'll eventually get to them all. And by other variables, I mean not the repeating variables. So here our choices would either be the drag force per unit length, which I'm using here, or the viscosity. That's the only other variable that is not a repeating variable. So the first step of this, rho to the a, v to the b, c to the d, times f primed. And notice we don't raise this to any exponent. If this is going to be a dimensionless number, it means that the dimensions of these 4 quantities, when combined together, have to all cancel out. So that's how we choose these powers, is we figure out what do those powers have to be so the dimensions of this group taken as a whole all cancel out, or in other words, so it becomes a dimensionless number. Well, the way we figure that out is we rewrite this side of the equation, but we substitute in the dimensions of each of these quantities instead of their variables. And so that's what we're seeing here. So first of all, we have the dimensions of density is mass over length cubed. So that's all raised to the power a. Likewise, the dimensions of velocity, length over time, all raised to the power b. The dimensions of chord length is length raised to d. The dimensions of our force per unit length, m over t squared. So notice all of these things we're getting from that earlier step where we listed the dimensions of each of our quantities. So when all that's combined together, the exponent on the mass, length, and time all have to be 0. Okay, so that's what we write on the right-hand side of the equation. is m to the 0, l to the 0, t to the 0. So this is what forces us to have a dimensionless number. So next thing is to find what these three powers need to be in order to give us a dimensionless number. So the exponents on mass have to add up to 0. So the sum of all the exponents on mass have to add up to 0. So we look here and we see all the places that mass exists. So here we have a mass, so that exponent is a. No mass here, no mass here, but here we have a mass and its exponent is 1. So we say that a plus 1 has to equal 0. That's the first equation that we get here in this little linear system of equations, and it's obtained by looking at the exponents on mass. The next quantity we look at is length. So length is a little more complicated because it appears in a lot more places in the equation. So here we have an L cubed in the denominator. So when we're adding up the exponents on length on the left-hand side of the equation, that gives us a minus 3a here. Minus because it's in the denominator, 3 because it's cubed, and a because this entire thing is raised to the power a. So a minus 3a from the density, just a b from the velocity, because this is in the numerator, so it's positive, and it's just raised to the power b. And likewise, the chord length is just length raised to the power d. Notice there's no length involved here, so we have no number at the end of that summation. So all of those things also have to add up to 0. Finally, we do the same thing with the dimension time. No time here, so there's no a ends up in this equation. Time in the denominator, so we have minus b. No time here. A t squared in the denominator here, so minus b minus 2 equals 0. So notice what this is. This is a small system of linear equations that we can solve for a, b, and d. And the solution is relatively straightforward in this particular case. We can tell by looking at this right away that a is equal to minus 1. We can tell by looking at this right away that b is equal to minus 2. And then we take those values for a and b and substitute them in here, and we get d of minus 1. So the solution to this little system of linear equations is a is minus 1, b is minus 2, and d is minus 1. So if we go back to our pi group here, we're going to take those exponents and rewrite this expression, but with those numbers in here instead of the symbols a, b, and d. So when we do that, we get that pi 1 is equal to rho to the a, v to the b, c to the d times our force. And when we put in those three exponents, we see pi 1 is equal to f primed over rho v squared over c. So this is our first pi group, or our first dimensionless number generated by the Buckingham PI theorem. So that all gives us pi 1, the first of our dimensionless numbers. But remember, we have two of them because 5 minus 3 is 2. So we go ahead and we do exactly the same procedure, but now we're getting pi 2. This part is the same, so our repeating variables will always be written down the same way here. We'll always apply 3 unknown exponents to them. But now that we're looking for pi 2, we put the other variable that we haven't used yet there. And again, just raised to the power 1. No unknown exponent required there. So we go through the same procedure again, and we'll do it a little more quickly this time. Notice that this part of this procedure, no matter how many of these dimensionless groups you're finding, no matter how big that number is, this part's always exactly the same because our repeating variables are always the same. So the only new part here is that we've got the dimensions of dynamic viscosity here. But again, We can build a little system of linear equations by looking at the exponents and adding up all the exponents on m, l, and t, and solving that system of linear equations. And in this case, we say that a is going to be minus 1 again. We see that b is going to be minus 1 as well. And if we take that a and b and substitute it into the middle equation, we find that d is also minus 1. So that's the solution to that system of linear equations. And we take that and we apply it to our pi 2 group, and we find that pi 2 is mu over rho vc. Because notice the exponent on all of our repeating variables is minus 1, so it's written in the denominator with just a power 1. So that's pi 2, mu over rho vc. So the last step of the Buckingham pi theorem is where we rewrite our original function in dimensionless form. So remember, this was our original function. So what the Buckingham pi theorem has told us is we can rewrite that as f primed over rho v squared c is a function of mu over rho vc. So notice what it's done for us here. Here we've got a problem with 5 variables, 5 different things that we need to keep track of. Force we need to measure, and 4 variables that we need to change to investigate how they affect that force. Whereas if we apply the Buckingham pi theorem to this, it tells us, you know what, you can simplify this problem. When you do your experiments, just vary this dimensionless group and it will tell you what this particular dimensionless force is going to be. So a much more compact and efficient way to represent the problem. So this is our first Buckingham pi result. And if you look at the right-hand side here, you might be asking yourself, isn't that the Reynolds number except it's upside down? And that's exactly true. That's actually the inverse of the Reynolds number. So the next thing we want to look at is some things that we're allowed to do with our dimensionless groups to convert them into a more familiar or a more conventional form. And those are called group manipulations. So after we've found these groups using the Buckingham pi theorem, we're allowed to do certain things to them in order to make them a little bit more useful, or more likely in order to make them more familiar to other people working in the field. So what are these things that we can do? Well, we can replace any group we want by itself raised to a power. Okay, so we can take any one of those groups and cube it or square root it or square it or do whatever we want, and that'll still be a valid dimensionless group. Because realize that doesn't change the fact that it's dimensionless. We take the entire thing and square it, that's no problem. It's still a dimensionless group. Other thing that we're allowed to do is take 2 of our groups and multiply them together or divide them, and then use the result to replace one of them. Okay, and we'll be doing all of these things as we go forward further on in this section. The other thing we can do is take a group and multiply it by a constant. Because if we double it or triple it or whatever, we're not changing the fact that it's a dimensionless group. So those are 3 things, or 3 group manipulations that we're allowed to do to our dimensionless groups after we've found them. So here's the result we have so far for our drag force on this airfoil. So we're going to apply a couple of these manipulations to get this into a more familiar form. The first thing we're going to do is invert this thing so that it is now a recognizable Reynolds number. Well, which one of the group manipulations did we use here? Well, realize we can replace any group by that group raised to a power. So I've taken this group, raised it to the power minus 1, in other words, inverted it. So this is a more preferred version of this because this is now a Reynolds number, a quantity that's very familiar to people working in the field. So the second group manipulation that we're going to do involves this dimensionless force on the left-hand side. So this dimensionless force has a name in aerodynamics. It's called a drag coefficient. Except the way it's written here is not quite the same as the way a drag coefficient is defined in aerodynamics. What we need to do to convert this into a drag coefficient is multiply the denominator here by 1/2. And so the group manipulation we're using here is that we can multiply any group by a constant. So I'm basically multiplying this group by 2, or multiplying the denominator by 1/2. So this now is a conventional drag coefficient. This is how we express drag forces in non-dimensional form. And the reason that that 1/2 is in there is because this quantity, 1/2 rho v squared, is the dynamic pressure that shows up in Bernoulli's equation. So it's conventional to non-dimensionalize the force by the dynamic pressure multiplied by some area. Now, normally we would be multiplying this by an area, but remember, this is a force per unit length, so we only need to multiply it by the chord length in order to make this left-hand side non-dimensional. So this is now drag coefficient is a function of Reynolds number, a very conventional way to write this in aerodynamics. So this is our first illustration of how we would use the Buckingham PI Theorem to guide us towards the appropriate dimensionless groups to study a problem like this. And it's brought us to two very, very conventional quantities in aerodynamics, a drag coefficient on the left-hand side and a Reynolds number on the right-hand side. Now, remember that step 6 of this procedure, we had some choice. We could have chosen a different set of repeating variables. So what I'm going to do now is rewind back to step 6 and look at an alternative, a different choice of repeating variables made at step 6. So we'll look at an alternate step 6. So let's say at that point we had chosen mu, v, and c as repeating variables instead of rho, v, and c. Well, realize mu, v, and c is still a valid set of repeating variables. We haven't chosen our dependent variable. And also, it's impossible to arrange mu, v, and c to form a dimensionless group. So it's a valid set of repeating variables. So if we proceeded with this choice, and we'll go through this a little bit quicker, our pi 1, again, would be the repeating variables, each raised to a power, multiplied by our dependent variable. We would go through the process of solving for a, b, and d. So again, repeating variables, each raised to a power. Our dependent variable here, just raised to the power 1. Set up our system of linear equations, and the result would be a of minus 1, b of minus 1, and d would have to be 0. So that tells us that our pi 1 group is f primed over mu v. And if you look at the dimensions of this quantity, you'll see that it is dimensionless as long as we've done the math correctly here. So with that choice of repeating variables, this would be our pi 1 group. Continuing on with our pi 2 group, we get again the repeating variable. So this part is exactly the same as when we found pi 1. And this part, the repeating variable, is exactly the same as pi 1. But now we have a density here, because remember, for this choice of repeating variables, the other variable we haven't used yet is density. So again, we go through the same process, and we find a new value for a, b, and d, which is -1, 1, and 1. And when we use those exponents to form a pi group, we get rho vc over mu. So notice this is the Reynolds number. There's not going to be any need to invert it. In this case, the Reynolds number has come out of this directly. So our final form of our dimensionless function for this particular choice of repeating variables is f primed over mu v is equal to some function of Reynolds number. So this is an alternative. Now, the convention in aerodynamics is to use the first version of this, where we got a conventional drag coefficient over here, but this particular choice also has some application in industry. If we were looking at the settling of very, very small particles in a fluid or in a gas, and that phenomena, the particles were small enough that that phenomena was dominated by viscous forces, it turns out that this is actually a very good approach, or a very good way to non-dimensionalize or to characterize the forces or the drag force on those objects, because we're using the viscous force here to non-dimensionalize it instead of the dynamic pressure, which is the convention in aerodynamics. So there's nothing wrong with this particular approach. It's just not the conventional way to express drag forces in aerodynamics. So that's a look at the Buckingham PI Theorem. And remember what it is. It's a way to take a phenomena and generate the dimensionless groups that are going to be relevant to studying that phenomena experimentally. So in the next video, we'll look at some variations on this. We'll look at a slightly more complicated situation where we add a few more independent variables and see how that affects our results.